we have a property P. We call it P, and that property depends on some integer n. And then we want to prove that P is true for all value of n. To do that, we have two steps. The first step is we find the smallest value of n for which the property holds. We call that value n0. So we have to find that value, and we have to prove that P of n0 is true. We call that the basis or the base case. And then the second part, which is the most important part, is the induction. The induction is we assume that P of k for some k is true, and then we try to prove that P of k plus 1 is true. So assuming P of k, we try to prove P of k plus 1. This is called the induction step or the inductive case. So this is the global scheme. And so why does it work? Well, if we can prove that if P of k is true, then P of k plus 1 is true. Because we prove number 1, we have some n0 for which P of n0 is true. Then we know that P of n0 plus 1 is true, but then P of n0 plus 2 is true, etc. for all the value n greater than or equal to n0. That's the way it works. So it's very easy actually to practice this. For example, we have a property Pn which says the sum of the first n powers of 2, which is like 2 power 0, 2 power 1, 2 power 2, up to 2 power n, that sum is equal to 2 power of n minus 1. Well, so we can prove that this property is true by induction. First, the base case. Pick n equal 1. So the sum of the first power of 2 is 2 power 0, which is equal to 1. Okay? And so that's exactly 2 power of 0 minus 1. So it's true. So P of 1 is true. Now, how do we do the inductive case? Very easy. We assume that the sum of the first k powers of 2 is equal to 2 power of k minus 1. And we try to show about the first k plus 1 power of 2. The k plus 1 power of 2 is actually the first k powers of 2 plus 2 power k plus 1, right? So this is what you see here. Okay, let me do this, and now let me do this. So this one is that the inductive, that the inductive assumption. The assumption says up to k, we know it's true, so it's equal to 2 power of k minus 1. And then we add this one. We had this one because that's 2 k minus 1 plus 1. And then we just compute it and we find the result. So the property is true also for k plus 1 if it's true for k. And so because it's true for 1, it's true for all the values. So here you have some example showing you some values actually. So it's very easy to check that it's true, right? And you see how we do it. Okay, we pick up the previous value and we add the new power, and we get, the result. A few words about powers of 2, because we use power of 2 a lot in computer science and in algorithm in general. So what is 2 power of n? Actually, it's a sequence of n bits and represent. So that sequence, if you take like n bits, you have like 2 power of n different values for that sequence, right? And basically, if you have a sequence of n bits, you can represent any numbers from 0 up to 2 power of n minus 1. And that's the way things are represented and implemented in the computer, right? And so we can ask ourselves, what about the, how much can we have using this power of 2? So 2 power of 10 is like a small value, it's about 1,000, right? We call like a kilo, like kilobyte. 2 power of 20 is like about 1,000,000, is what we call mega, in the computer language. And 2 power of 30 is about 1,000,000,000 already, which is commonly called a gig, okay? Giga, right? And so actually, we can see that with pretty small value of the power of 2, we can encode a lot of items. For example, it is easy to give a unique number to every person in the United States using only 29 bits. So if we have like a binary word of length 29, we can, using that number, those numbers, we can give a unique ID to each person in the US. If we increase a little bit the power, we move from 29 to 33, we can give every person in the world a unique ID. Actually, we increase a little bit more. We have 2 power of 38, which is an estimation, of course. Then we can give an ID, a unique ID, to every person to have ever lived on Earth. Means right from the very beginning. So now, means what? That if we increase more the power, we get the absolutely huge numbers, right? For example, 2 power of 200 and something will be the numbers of the number of numbers we need to give a unique ID to every atom in the universe, which is of course huge. So this makes us understand that if you have a password, for example, which is like a number encoded in 128 bits, well, there is absolutely no way that anyone can discover that password by trying all the passwords, because there are much too much passwords to try. So power of 2 are, big numbers. Now a few words about some very useful functions like logs and exponents. You know those functions, of course, so this is just a review, a quick review. We are much interested in the log of base 2 because that's the normal base in the computer. Actually, we don't mind having log in another different base because we can change the base of the logarithm, so it's not a problem. So the log function is the reverse function of the exponent function, right? And so log of x is equal to y if x is equal to 2 power of y, right? And so, for example, log of 1 million is like a little bit under 20, right? So just as exponent function is growing very quickly, the logarithm function is growing very slowly. And you will see that this is a very important fact we use when we analyze the complexity of the algorithms. Okay, so this is what we see here. So we can see different graphs here, which shows us, the growing the function. And so log of x is much smaller than x as x is growing. So you see on that graph that as n is growing, log of n is keeping very low, okay, very small. We will see how we use that in practice, right? Okay, so this we have already. Okay, you probably know the properties of the logarithms function already, so it's easy. I don't detail this because it's easy. At some point we may have to mention that function, which is like very special. That function is log of log. That function is extremely slow in growing. And it grows as slowly as 2 power y is growing quickly. So that function is like almost constant because, to make it growing, you have to increase x by a huge number because else log of x doesn't grow too much. Okay, like I said, the base doesn't matter because we can change it by a constant. Okay, so the rule is log of x in base b is equal to log of x in base a divided by log of b in base a. So the changing of the base is only a constant factor. It's just like you multiply the log by some factor. So we don't care about the base, and the default base we are using all the time is 2 because in the computer that's the preferred base we use. Okay, some more useful functions like the floor and ceiling function. Those functions are stupid, right? We all know those functions. Well, they are mentioned once in a while in the calculation we're doing, so we just review them quickly. So the floor function, the ceiling function, just to cast from real value to an integer value. So very common function. We have some properties we can summarize on the slide. So for example, if you take the floor of n divided by 2 plus the ceiling of n divided by 2, you get n. For n equal an integer. Okay, so this is about the review of the function. Means you don't need to know any special mathematical construct to understand and to work on the algorithm analysis. You just only have to know the basic functions you know already, and the function we will emphasize on will be the log and the exponent. The log is very important because we have a lot of algorithm for which the complexity involves the log function. So we will mention the log function a lot, but it's very easy. And that's about all the mathematical tool we need. We will see that we have to understand like some recurrence, but we will see that a little bit later. Okay, so what is algorithm analysis? Well, an algorithm is a method to solve a problem in the computer. So it's a method that can be implemented inside the computer, and the computer will just run that program to solve the problem, right? The algorithm describes the method we use to solve the problem. So it's a kind of abstract view of the implementation of the actual program you write in a given programming language, right? So what is algorithm analysis about? Algorithm analysis is about understanding how the complexity or the size of the algorithm grows as the input grows in size. So, for example, let's suppose we have a very simple algorithm. You have an array which is not sorted with value inside, and you want to check if one item is inside the array. The algorithm to do that is very simple. It's just check all the cells of the array from the first to the last, right? What we want to try to understand is, so if we design an algorithm to find an item in an array, what happens? So we have an array of some size. We run the algorithm, we get some time. Okay. Now, what about if we double the size of the array? What about the time of the algorithm taken by the algorithm? Well, that time being double to, or more, or less. So what we try to analyze is we try to understand how the complexity of some algorithm will change when we increase the size of the input. This is what we want to study. We have some algorithm to solve some problem for some input, and we want to understand how the complexity will change as we change the size of the input. This is what we want to study, actually. So this is what we call the algorithm complexity. The complexity of the algorithm is related to the running time of the algorithm, right? Now, there is another aspect, important aspect, is how much memory do we need to run the algorithm. So actually, those are the two key aspects. When we talk about algorithm analysis, we're interested in the time, how much longer does it take to run, and we are also interested in the memory space, how much memory does the algorithm need to run. Okay, those are the two aspects. Now, those two aspects are not equal, and the most important is the time, not the space. The reason for that is that nowadays we have a lot of space in the computers, right? We have a lot of memory, a lot of RAM memory, a lot of disk memory. So memory is no more an issue too much, and actually it's less important than the time itself. Now, there is a separate issue, which is the algorithm correctness. What we're talking about here is about the complexity, so about the running time. The correctness is completely different. Is how can we ensure that the algorithm is producing the right result? And this is much more complex. Actually, we don't focus on that problem in this course because, well, we try, of course, each time we design an algorithm, we try to give some hints, some proof that the algorithm is working and producing the right result. But we don't have a formal method to do it. For the complexity, yes, we can do it. We have some formal tools to compute that complexity. And so we can compare the algorithm together, and we can choose between two algorithms, and we can choose the best one, the one which has the less time complexity, for example.